Okay. Welcome to EE 123, Lecture 9. Woo! Thank you. Okay, so today we're going to talk about spectral analysis using the DFT. And I thought I would just start with a demo. So the demo I'm going to show you is using what's called GNU Radio, and in particular GNU Radio Companion. So it's just kind of GNU Radio is a piece of software, open source software, that implements software-defined radio in a very efficient way that everybody can take basically samples and then process them on a computer and be able to play with different type of modulation, demodulation, and other types of signal processing. But it's all built toward a streaming type of application. What's nice about it, so it's written very efficient libraries of C++, Fortran, and so on and so forth, but it has Python wrappers that you can integrate. And then you can also have this GNU Radio Companion, which is a graphical interface where you can, much like Simulink, where did it go? Much like Simulink, put different parts, different objects, control their parameters, and go through different type of processing, which is kind of fun to play with. And so you create really interesting systems. And they built for you a lot of, for example, filters, bandpass filters, FFT filters, so on and so forth. You can open files. You can decode digital television. You know, if you have some digital TV that are coming in, you can code. You can do also bytes operations, so on and so forth. And you can add this and build very complex systems just by, connecting lines. What I did here is I did a very simple thing where I took an audio source, connected to a GUI that computes the basically the spectrum, and then a signal source that puts out an audio signal. Okay, and I can control that. There's a slider that I can add. And so this very simple application took me about 3 minutes to create, and it produces this thing. Okay, so now what you see here is a spectrum, and the spectrum is computed over FFT size of a 1024, and you can change that. And then you can use different windows, which we're going to actually talk in a second about. What is the main windowing? Okay, so I'm going to multiply my chunks of signal that are coming in with a certain window, and that's going to have certain properties to this. Okay, so when I look at this is a spectrum, and of course the spectrum is dynamic because the spectrum changes over time. Okay, and it depends on the block size. So if I whistle, you can see the frequency showing up. And when I speak, you often see a few harmonics, not just necessarily one, because my voice emits not just a fundamental harmonic, but more harmonics. You see there's a few more over there. But you can't see them very well because we don't have enough spectral resolution. So we can increase the spectral resolution by taking a larger window, and then I can go, So you see things a little bit more in detail. Okay. Of course, it slows down because now I take bigger chunks of windows, and so now I have to wait for the samples to arrive. Okay. So a few other things that this could be, for example, interesting. I can. Here's an application where I play a certain tone. Let's switch to play a tone. This is quite annoying. Let's go to something I can't hear. There you go. Okay, so I can pick up the tone, and depending on the different window size, you see how the resolution of the I have an improvement in temporal resolution, right? But the resolution of the spectrum is worse. Can you hear it? Okay. How about that? Okay, good. So I increased it to about 18.6 kilohertz. Okay. Yeah, that you'd be a dog to hear this. or like 5-year-old. Okay, so you see that the resolution is not very good, and as I increase the size, yeah, the resolution is much better. I can resolve it better. But at the same time, I lost some temporal information. Right? And we're going to see that when we're going to do time frequency analysis, there's going to be a trade-off between these two. Okay, so it's quite obvious. Let's go back here. Other thing that's interesting is, you see this? Yeah, that's the Doppler effect. Yeah. So you can actually see this in what's called a waterfall diagram. In a waterfall, we're talking about spectrograms. And basically, it's spectrum over time. And now you can, let's scale it. Right? You think this is cool. Okay, let me stop this for a second. And let me play the audio here. And put it on over there. Okay, ready? So now, this is continuous wave radar. Okay, you send a continuous wave. It hits my hand, is reflected back into the microphone. Because I'm moving, it's Doppler shifted. And then if I put a filter in the receiver over this fundamental frequency, then I will just see the reflections. There's only stuff that's moving will will receive a signal. So this is called continuous wave radar. It's used quite often in different applications. There's also pseudo-continuous where you send short pulses, and then you can kind of also get the range. This only gives you velocity. Okay, but now I created a kind of a velocity detector, right? Yeah, so I can aim it. Like if I have a directional microphone, I can now aim it at a certain direction, and then make basically a range, like you know what the police would use for. Like a radar gun, but audio, okay, like an audio frequency. This is exactly how the radar gun works, only in RF, okay, frequencies. Similar way, okay. Okay, so this is really cool stuff that you could do with audio. I can do gesture recognition, maybe. If I use 2 speakers, maybe I can get some information in space. If somebody wants to do a project on this, you're more than welcome. Okay, you can also probably detect a range. And one of the lab that you're going to have this week and the next that you're going to work on, you're going to create a pulse radar. Okay, so a sonar effectively. You're going to send pulses, you get reflections, and you're going to range it. You can combine this with velocity, or take all this together, and you have a really nice maybe user interface that you can maybe create. Okay, using signal processing. And you can use this kind of framework probably to do this. Okay, any questions? This is a really nice tool. I really recommend using this, just playing with this. The GNU Radio Companion in GNU Radio. I'm going to close it. Enough fun. Now it's just going to be like boring stuff. Not really. We'll talk about the details. What does it mean? What is actually, if I want to measure a frequency, what does it take? What's the resolution I'm getting it, and so on and so forth. Okay, but this was kind of like a cool thing, this demonstration. But on silence. All right. Okay, last time we talked about FFT, fast algorithm to compute the DFT. That allows me to do this in real time. Okay, imagine if I picked a 6,000 something window and I have to do it n squared. We'll be just like, oh, yawning. Or this thing would get really hot. Okay. Today we're going to talk about frequency analysis with DFT. We're going to talk about the effect of windowing, as that gives me the trade-offs between spectral resolution and the ability to differentiate sensitivity between different spectrum that might be close together. And then we're going to talk about the effect of zero padding, which is effectively nothing. Nothing in terms of information, but it's really just beautiful. Well, it helps you look at things, but not necessarily helps you add more information. Okay, so you ready? Okay, so we're going to use the DFT to analyze the spectrum of a signal. Okay, and yes, it appears to be simple. You take a signal and you compute the DFT, and you look at the spectrum. Okay, but there's trade-offs. I mean, there's all these subtleties in DFT, that really in digital signal processing that you have to take care of, because you're approximating things sometimes, or you make because you're dealing with discrete signals and discrete time and finite signals, then you gotta be careful and understand what is actually going on. So we're going to talk about what is the signal. What is the trade-off between signal duration and spectral resolution? You kind of saw it a little bit, right? I took a larger signal duration. I got better spectral resolution, but I lost temporal resolution. The signal sampling rate versus the spectral range. When we talk about sampling, we're going to talk about this more. Okay, not so much today. Okay. Spectral sampling rate. Okay. I mean, you compute a spectrum. The spectrum, we also want to represent it on the computer. We're going to discretize the spectrum as well. Okay? So we're going to approximate or sample the DTFT effectively when we display it. Okay? We're not going to continuously display it, right? And then we're going to talk about some spectral artifacts that are associated with the fact that we are taking things over a finite time. Okay? There's no such thing as a pure frequency when we're talking about finite time, because it changes. All right. So we're going to consider the following processing of continuous time signals when we try to do the spectral analysis. Okay, you've got this continuous time signal coming in. We're going to what's called anti-aliasing low-pass filter. We're going to filter high frequencies because we're going to sample it. And when we talk about sampling, we're going to talk about this in more detail. So we get now a signal which is band limited. Okay. It doesn't have certain high frequencies above a certain frequency. Then we're going to convert that from continuous to discrete time. Okay. And we're going to get a discrete signal, which is going to be multiplied by a certain window, because we're going to look at a finite range of samples. Okay, so Wn is a window of time that we're going to look at the signal. And then we're going to compute the DFT of that to get V of k's. Okay? And of course, we can compute this using the FFT. Okay? Any questions up to here? Pretty straightforward. Moving on. Okay, so now we're going to have some tools here that, there's a few parameters that we need to pick in order to come up with some spectrum, right? And whether that spectrum makes sense or not, and whether that's going to allow us to use it for a particular application that we're looking for or not. And it's going to depend, of course, on the application. Okay? So if you apply a window to the input signal, that will reduce the spectral artifacts. Okay? And I'll explain what does it mean. But applying a certain window will reduce those effects. Okay? Padding the input with zeros will increase the spectral sampling. Okay? So those are really the tools that we're going to be using. So here are the parameters. We're going to sample at a particular rate. Okay? Sampling at a particular rate means that we cannot represent frequencies that are higher than something related to that rate. Okay? And it turns out there's going to be, what's the sampling rate? Twice the highest frequency. Okay? So I can only represent half of 1 over t in terms of frequencies. Okay? Half of 1 over t I'm going to be able to represent. Actually, the whole bandwidth, if you take negative and positive frequencies, it is 1 over t. It's just that the highest frequency is 1 over t over 2. Okay? But you have the positive half and then the negative half. And if you had a complex signal, right, then you can you would see a whole range of 1 over t hertzes. Okay? The range will be 1 over t hertzes. But the maximum frequency will be 1 over t over 2. Does this make sense? But the bandwidth is 1 over t. Okay, so we're going to have a sampling interval and corresponding sampling frequency. So it's in radians 2 pi over t, or in hertz it will be 1 over t. We're going to pick a window length, which doesn't have units. Okay, this is going to have a certain window duration over time. When I've got, the thing is, I need to remember what I did. Because when I give you samples, you just don't know, what is the time interval. So you need to remember what was the sampling frequency for you to remember, to correspond it to the particular time. Okay? So you have to remember that. So window duration is L times t, and that is in seconds. Okay? And the thing is, I give you signals, right? Digital signals. That's the problem, is that you just don't know where they're corresponding to. So they're all normalized to a normalized frequency, or a digital frequency, which is going to be small omega, that goes from minus pi to pi. Or a digital frequency that's not omega, which I call often k, which goes from minus half to half. You just divide omega with 2 pi. Okay. The DFT length is going to be of size n, that could be equal to the size of the window, but could be bigger than the size of the window. And when it's bigger over the size of the window, that means I'm zero padding. So I did take a window of the signal, but when I compute the DFT, I might compute it over a larger range, only I'm going to zero pad it. Okay? That's strange. Why don't you just take a bigger window? Right? Well, there's going to be a reason for this. The reason is that we're going to get better sampling of the DTFT by doing this. Okay. Again, DFT duration. Now, what's important is the spectral resolution, my ability to resolve frequencies. Okay, what is my resolution in the spectral domain? And that's going to depend on how long is the window. Okay, when I took 16,000, I had better spectral resolution than I took 4,000, 1,000 samples. Okay, that gives me my spectral resolution. Okay. But that is different than the spectral sampling interval. Okay, because I could take a window of 10,024, right? That would determine a certain spectral resolution, which is going to be proportional to 1 over that, 1 of the length. But I can then take that and zero pad it. Did I improve my spectral resolution? You'll see that we don't improve our spectral resolution. But we sample the DTFT more finely. Okay? So it's just making the DTFT plot nicer. But it doesn't improve the resolution. And I kind of showed it to you when I used a smaller size window, everything kind of looked a little bit rounder. Right? All the peaks that were sharp in the large window, they were kind of became rounder and like kind of more spread out when I used a smaller window. But when I displayed, I actually interpolated it. And interpolating, that's what means zero padding. And you'll see that. So here's some examples. We're going to consider this example where we have two frequencies with two amplitudes. Okay? The continuous time Fourier transform of pure frequencies are delta functions, right? Remember that? Back in 120? 20 even? So each frequency, because it's real, is going to have two peaks, one in the positive side of the frequency and one in the negative side of the frequency. And they're going to look like this. Okay? So they have, I don't know, what is this? 5 hertz and 7 hertz? Something like that. 5 hertz. And we're going to see two peaks. And it's exactly the plot that I showed you before, only not, because this is continuous time. Okay, imagine that this was continuous, actually 3.5 hertz and 6.5 hertz. Okay. And then this is the plot. Okay, ready? Okay. So now we're sampling that signal. Okay? When we sample that signal, okay, now we have a discrete time signal. And I don't remember if we showed it to you when we talked about the DTFT. There is a relationship between the DTFT and the continuous time Fourier transform. And effectively what you get is kind of a wrapping when you sample. We're going to get to this when we're going to talk about sampling. But now, once things are discrete, you've got a periodic signal. You've got a periodic signal that has a Fourier transform, or the DTFT, a discrete time Fourier transform, that has some relationship to the continuous time Fourier transform, where omega equals capital omega times t. More in chapter 4 on this. But effectively now it repeats every pi. Okay? Effectively now every 2 pi. Okay? Now omega goes from small omega goes from minus pi to pi and is repetitive. Once we have discrete samples. Right? And we showed it to you that when you have a discrete case, when you compute the DTFT, you've got something that repeats every 2 pi. So if we look at the plot here, and if let's say we sampled at about 20 hertz, then that would correspond to a maximum frequency of 10 hertz that can be represented. Okay? So it will repeat, the spectrum will repeat every 10 hertz. But if you actually take that 10 hertz and multiply it by t and multiply by 2 pi, and you will get your omega. Effectively, this will be 0, and that will be pi, and that will be 2 pi, and so on and so forth in discrete frequencies, okay, or discrete angular frequencies. Okay. So now the DTFT of this sampled signal, or the DTFT effectively of those samples, looks like this, where this is 0 and this is pi, 2 pi in omega, right? And it repeats over and over again. Actually, 0, pi, 2 pi. Okay. Any questions? All right. Okay. So in a real system, we sample mostly on a finite block of samples when we want to compute the spectrum, right? We're not going to we're not going to take something infinite and then compute a DFT on it. It's just not, doesn't make sense, right? And even the example that I showed to you, I picked the window size, right? I had to, right? Because I had to display something. Right? So I picked the window size. So we're going to pick a finite block of samples. Okay? X of n, which is the evaluation of the continuous time signal at t equals nt. Okay? And the size of the window is going to be size L. So an L-size window of samples. There you go. Do something with them, please. Show me a spectrum. How about that? Okay? There you go. Now, if you think about this, I multiplied with a window. A square one. But the fact that I chose L samples out of the signal, I can describe it mathematically by multiplying with a rectangular window of that size. Okay? That did something. Because when I multiply two signals together in the time domain, or the samples domain, or the sequence domain, what does it do to the frequency domain? No. A circular convolution. Big deal. It's a difference. This is subtleties of this. This is the subtlety of discrete time. Okay, it is a circular convolution. It's not a convolution. It's a circular convolution, continuous in the frequency domain. Okay, it's different. Don't forget that. Lots of problems could happen. Like you can miss this satellite because of that. I don't know. Because of a side lobe that wraps from the other side. I mean, there's issues that you have to deal with when you talk about discrete time. Okay, one of them, you have to realize it's a circular convolution. Okay, it's not linear. Sometimes it can be approximated as a linear convolution. And we showed actually when it doesn't have to be even approximate, it could be exact. Okay? When the bandwidth might be finite. But if it's not finite, there's just no way for you to get away. Anyway, so remember that in homework 1 we looked at rectangular versus triangular window, and we looked at what happens there, right? So we are actually multiplying by the window. Okay? Okay. So we take a block of signal and we multiply by a certain window. Okay? Now it could be that it is the rectangular one, but it doesn't have to be. For example, we can pick a triangle or a baby shape or a boa constrictor shape that eats an elephant. You can pick your favorite window. But let's suppose that the window has a certain DTFT. Hey, watch out there. Let's say it has a particular DTFT. The window has a DTFT which is W e to j omega. So the window block of samples has a DTFT that is given by the periodic convolution or the circular convolution of x e to the j omega and w e to j omega. Okay? So we have to compute the convolution in order to see this. So there is already implications of the size of the window and what's going on. So the convolution is going to have an effect of the spectrum. And it's going to have two main effects. The Fourier transform of the window is going to have a main lobe, and it's going to have side lobes. The main lobe, main effect, is going to be, if I convolve something with something wide, it's going to give me something blurred. Convolve with something wide, give me something blurred. That's the resolution. Okay? That's why when I pick a smaller window, turns out that the main lobe is going to be wider, and I'm going to get more blur. It also has side lobes. And the side lobes going to give me kind of leakage. Because what does it mean that a side lobe is? That if I have a peak here, that's going to affect peaks over there. Because when I convolve, peak over here is going to have resulting values over here. So that's spectral leakage. Okay? And it turns out there's always a trade-off between these two, spectral leakage and resolution, when you're talking about linear reconstruction, linear type of analysis. Okay? Not when you do something nonlinear, but there is, for the linear case, there's a trade-off, inherent trade-off between this leakage and so on and so forth. And this comes down to be this time-frequency uncertainty principle, Eisenberg principle, that appears in many, many situations, is that you cannot really figure out both the frequency and the time resolution at the same time. There's always going to be some uncertainty. Because as I zoom in time, I don't see frequency. When I zoom out in time, I can see the frequency, but I don't see the time. Okay? So we're going to look at different windows. People have looked at different windows for this analysis. Okay? And the classic teaching of DSP is they show you all those windows, and then they tell you here's the optimal one at the end. Why go through all of this? Because sometimes it's just easy. And in many situations, people just use certain type of windows. So it's good to be familiar with them and what their properties are. Some of them are ad hoc. But now, these days, we know how to generate something based on optimality criteria. Okay? And it's not now. It's actually been resolved a long time ago, too. So here are some values, some examples. A boxcar, which is a rectangular window. This is the MATLAB command for this. And you always need to look at what this actually is the definition. is a rect, is a boxcar. Sometimes it has one more, one less. I don't know. So you have to check what it really is in order to really understand what is actually going on. Okay? So it's 1 between m over 2, and it's equal to m over 2, and then 0 elsewhere. Okay? Triangular window looks like this. Okay? Bartlett window, it's also a triangular window. But if a triangular window doesn't have a 0 over here, the Bartlett one would. Okay, it's a little bit different slope that it's picked up. Okay, so you have to look at those definitions. This one has a 1 here, and this one doesn't. They're similar, same, but different. Okay, and so the result is going to be slightly different. Hand window is defined as a raised cosine. So you take a cosine and you raise it. You raise the cosine. Okay, and so it's very smooth. It's infinitely differentiable. Okay, so it has good properties in terms of spectrum. If something is really smooth, the spectrum is going to be kind of like also smooth. Okay. Hamming window. Oh, I get Hanning. Okay, this is a joke, by the way. I forget. There's a story about this in one of the DSP books about Han and Henning. So it was Han, but there was this guy called Hamming, and so somebody wanted to make a joke about this Han guy and call him Henning, and actually it stuck. And then now in MATLAB it's even 2 different windows, but it was the same person. It's actually called Han. Okay? And the difference, I guess, is +1 here. But it's a raised cosine. Okay? And MATLAB has these differences. I do not actually what's going on in NumPy. Okay, but you have to check by doing help. Hamming is slightly different. You just also raise it a little bit more. Okay, so it's still a raised cosine, but it is raised a little bit more. See? This is not 0 here, and it's just a little bit higher. Okay. That's Hamming window. These are very popular windows. Hamming and Hanning or Han or whatever you pick. Very popular. All the windows that we use are often real and even. Okay. And because they're real and even, they're going to have a DTFT which is real and even. You remember all these properties, especially for next week. Okay. Real and even, odd, what does it mean? Odd and even, odd and not even, conjugate, not conjugate. All of this, you need to I wake you up in the middle of the night, and then you get really upset because I shouldn't be waking you up in the middle of the night. But at the same time, you really need to remember this. And you probably will wake up all in the middle of the night anyway, because I've seen you on Piazza. Okay, so it is real and even, and it's periodic with omega, with a period of 2 pi. So I'm going to show you a few plots, but what I did when I showed this plot, I normalized the window at DC to be equal 1 so you can compare them. Okay? So I normalized just to make it easy to compare. So let's take a look. Here are a few examples. This is m equals 16, so the size of the window is 16. Okay? This is a boxcar and a triangular window. Okay? Boxcar and a triangular window. This is in linear scale, and this is in log scale. Okay? Linear scale and log scale. And what you see is that there's a couple of things that are really interesting here. One is that the boxcar window has a very narrow main lobe. In fact, it has the narrowest main lobe you can ever imagine possible. Okay? By definition, it is the narrowest main lobe. At the trade-off of increased side lobes. Okay? The side lobes are significant. The side lobes are significant. Okay? And you can see that. They don't decay very fast. They, in fact, decay as 1 over W approximately. Approximately 1 over W. The triangular, which is in fact, if you look, what's the Fourier transform of a triangular window? It's the square of the Fourier transform of a boxcar. So of course things will decay faster because whatever decayed at 1 over omega now decays 1 over omega squared. At the same time, it widens the main lobe. Okay. How does this compare to Hamming and Henning? Well, Hamming and Henning, if you look at the second side lobe of a boxcar, I mean it's around minus 17 dB, which is not much. I mean, it's pretty high. If we're talking about the Henning, it's minus 31 dB. Okay, dB is, this is log scale. So the fact that it increased from 17 to 34, that is significant. Okay. What about the Hamming? Hamming, so here's the difference between the two, and this is actually very interesting. And it's going to depend on your application where you want to use one or the other. So the Henning one has a narrower main lobe, so it gives you better resolution. But it has a higher side lobe. But at the same time, the side lobe decay quite fast. So if you want to distinguish between things that are far away, it's actually pretty good because the side lobes decay quite significantly as you go further away. The Hamming one has a second side lobe, which is much smaller. It's about minus 40 dB, the second side lobe. But the trade-off is that you have a wider main lobe, not by much, but unfortunately the side lobes don't decay. They remain constant. So, that's going to definitely interfere maybe with something that's far away. Okay? But it will be able to resolve better things that are close because the second side lobe is lower. Okay? So these are trade-offs.
Why do you have that result? Why one of them goes faster?
That's the DTFT of them. That's how they're designed. But there's always going to be a trade-off. One's going to be fatter or like bigger side lobes, and there's always a trade-off. And depending on the application, you want to use one or the other in order to look at your analysis better. Okay? Questions? And you see all those applications that I showed you for spectral analysis, they have all these windows there, You can pick and so on and so forth, and you can pick the size. And all these parameters do exist there, so this is real. Okay. So here are the characteristics of the main window types. So you have the rect window. The main lobe is always 4 pi over m plus 1. So as you increase the size of the window, and m is here the size of the window, then the main lobe is decreased. Okay? So you can always make the main lobe narrower by taking a larger window. Okay? You can always do that. Side lobes are quite big, okay, minus 21 dB. And Bartlett, when you actually use Bartlett, it doubles the width of the main lobe. Okay? All these have double the width of the main lobe. Okay? So at the expense, of course, of reducing significantly the side lobes. Okay? Blackman actually has an even wide lobe, but look at the side lobes. I mean, they're ridiculously small. 74 dB. It's huge. Okay? So what I do recommend is always check what's the definition of M when you compute, and what's the definition of the window when you actually use functions. Okay, here's our examples. So let's consider several examples. Sampling rate is still 20 hertz. Okay? And we're going to look at a rectangular window, L equals 32. Okay, the size of the window is L equal 32. The DTFT of a rectangular window looks like this, where this is 0 and this is 2 pi. Okay, 20 here is omega over 2t, but it's 2 pi. Now this is the sampled signal that I used before. Remember the two cosines. This is a sample signal, and that will be the DTFT of the windowed signal. So only taking 32 samples and then computing the DTFT. And you can see that instead of getting impulses, now you have some width. And you see also, right, the ripple, the side lobes, because of the rectangular window that we chose. You want to try triangular window? You want to try? Yeah. Let's try. Okay. So I add a triangular window. If you think of what a triangular window does, it really chooses it tapers, it basically makes a smaller window, but it kind of still uses some of the far away. I mean, it tapers off, right? So it's an effective smaller window. That's why things become wider. Okay? But then there's no sharp changes, so the ripple decreases. It's another interpretation. So now things look like this in the time, or the sample domain. You've got much wider peaks. Okay, the peaks are not as small anymore, but the side lobes are significantly reduced. Okay. Hemming?
Why do we have that trade-off one more time? You said larger main lobe, less side lobe.
I mean, if you think about this, what is triangular window? I mean, it gives more emphasis to the middle of the signal. So it's really just using an effective smaller number of samples, right? But the fact that you also multiply by window is a convolution in the frequency domain. It's a convolution with a triangular function that is wider than a rectangular function. Okay. Hemming? Oh, look at that. Gorgeous. Gorgeous. So the nice thing about Hamming, actually, that it has very similar main lobe as triangular window, but at the same time has much smaller side lobe. So it operates in a better trade-off. Okay? And so you get really nice depiction of peaks similar to the triangular window, at the same time much lower side lobes. Okay, so now I want to improve it. Okay, this is too much of a hit on my resolution. So what can I do to improve my spectral resolution? What? Resample. Increase? Increase L. Increase L. That's right. So if I increase L to 64, I double my spectral resolution. Ooh, yeah. See? Double it. Nice. What did I lose, though? Time. So if my signal is not stationary, changes over time, I lost that resolution. Okay. Now, these are all just ad hoc windows, but there's also other windows that people have developed which are more optimal. For example, the Kaiser window, it is designed to have a minimum main lobe width for a given side lobe energy percentage. Okay? So it minimizes the integral over the side, so the energy over the side lobes divided by the total energy. Okay? It is parameterized by L and beta, and it uses a Bessel function in order to create the window, which is parameterized by beta, and you can look in the book at exactly how it's parameterized. And for a given trade-off, you have a table which lets you pick up the parameters that you want. Okay, but it will be optimal in terms of minimizing the energy of the side lobes. Right? There's another window called Dolph window, which minimizes the peak. Okay, the peak side lobe to main lobe ratio. That's a different optimization, right? But it's kind of similar to the Hamming and Henning, right? If you think about this, Hamming kind of have a maximum side lobe that's constant. Henning kind of decays. So there's a trade-off there. So it's a similar thing. You can look at the book to basically determine what is beta and L for a particular set of optimizing factors. And here's just an example. And you can also download the IPython notebook that I generate those plots. Okay. So here are two frequencies. One is 2 pi 0.1n plus 0.005, right? So there's a factor of 200 smaller signal of peak with respect to this one. And I'm going to look at a window of 128. And if I just use a rectangular window, there is a frequency here that's pretty obvious. That corresponds to this one. There should be a frequency here. And I kind of see a disturbance in the force. But it's not clear, right? You can't really see it because the side lobes just overwhelm this small component. I'm not talking about the case of noise here. There's no noise. It's perfect. I mean, it's just like pure frequencies. No noise, I cannot see it. Right? That's a problem. Okay? If there's noise, that's, I don't know, even more disturbing. If I use a triangular window, there's bigger disturbance in the force. Right? When I use a Hamming window, still not there. And you know why? Hamming window has lower side lobes, but the side lobes are constant. So it's still, what is it's 30 dB or something? The Hamming side lobes or something? Was it 30? 37 something? It's just not enough to be able to resolve this very well. So this is Hamming. This is Hen. Okay? When you use a Hen window, now it starts showing up. And the reason it's showing up is that the side lobes for Hen window, when you go further away, are almost 100 dB down, way below that frequency. So you can now start seeing it up. Right? The force is with this one. You have, so look at, first of all, the main lobe is quite wide, but because they're further apart and you can use this, then you can actually detect.
Did you say that two main lobes?
Yes. Yeah. Now, if I use a Kaiser window with the beta equals 6, that corresponds to approximately this, I get slightly better. Okay. And I can improve to beta equal 9, which makes the main lobe a little bit wider, but definitely resolves this one. Okay? So this ability allows you to be able to distinguish between them, as long as, by the way, the noise level is lower than this guy. Because if the noise level was higher, then there's no way you'll be able to resolve it. You'll just see that and then flat. Okay? So you got to be aware that this is analysis without noise. Okay? But the fact that you have this interference between these components, that's a big deal. Okay? And you have to be, and there's different ways that you can mitigate, and there's going to be trade-offs. Okay, I got 2 more minutes. I want to actually talk about zero padding because I don't want to spend it more. Well, I have lots of slides. Oh boy! All right. So, what is really zero padding? If you think about this, if I have an infinite sequence, and I just take a window, I multiply by a window, right? And I have an infinite sequence, and I basically compute the DTFT. Right? DTFT I compute over an infinite sequence, but most of it is 0. So even the DTFT, I only use that window in order to compute it, right? So what is adding or zero padding effectively makes? You just get closer and closer to the DTFT. When you do a DTFT of an infinitely large window, it effectively becomes like the DTFT. Okay? So if I make it twice, I get better and finer and finer and finer estimation of the DTFT, and we showed it to you in the DFT lectures. Okay, so the effect of zero padding is really just sampling better the DTFT. Okay, just sampling it better. So One thing about the DTFT is that the ordering of the DFT is unusual. DFT zero frequency is in the first one, is the first index. Okay? And not in the middle. Okay? So when you show things, this is the DFT of that sequence. This is the DFT, and you see that now things are kind of flipped. This is zero frequency, that it increases, and now those are negative frequencies, corresponding to negative frequencies. Okay? As I increase, so here what I did is I pick L equals 32 and N equals 32, and this is the endpoint DFT, and you see a certain sampling, and this is the DTFT, and you see that it follows it. It really samples it. When I zero pad, I added 0 here, I just get a finer sampling of the DTFT. Okay? I just get finer sampling of it. Okay? Now, in order to go and show the DTFT, I need to do what's called an FFT shift, which take this part, put it over here, take this part, put it over here. And there's functions that you can use. Let me steal one more minute from you. Here's an example of the effect, why zero padding actually doesn't give you more information. It just gives you better sampling. Here's an MRI of the brain. This is the 2D Fourier transform of this MRI. Yeah, there is a 2D Fourier transform. I'll talk about this. But this is the 2D. What I'm going to do is I'm going to crop from the low frequencies a rectangular window. I'm going to reconstruct it using a DFT. I get this tiny image. This is a DFT of 20. I get this tiny image. Now I'm going to take this and I'm going to zero pad. Just add zeros, the same size as this. Okay? So I cropped it. I added zeros. I compute now the DFT of 200. So zero padding. This is what I get. I get a bigger image, but I don't get more information. It's still low resolution. That is exactly what's happening when you zero pad a signal. You cannot resolve frequencies better. But you just zoom in. You kind of just display them on a bigger screen. Okay? One last thing. Truncation artifacts. The fact that you crop and you do a rectangular window. Here's a case, an MRI of a spine. A 40-year-old patient with a history of lower limb weakness referred for an MRI screening of a brain and a whole spine for cord. MRI sagittal of T2 screening, shows a faint, uniform, linear high signal at the center of the cord. You see, this is the spinal cord, and then there's this line in the center. You see this line in the center of the cord? This line in the center. Normally, it should be constant. This could be what's called syrinx, a spinal cord disease. The question is, what is the case here? Cord demyelination, syrinx, or an artifact? Okay, there's not much time. What I'm saying is, it is an artifact. It is actually Gibbs ringing. It's a truncation artifact because we don't acquire high frequency enough. So this is a low resolution. I cropped the frequency and I computed an inverse Fourier transform. The fact that I have a spinal cord here, this is really bright. This is bright. So there's ringing around this bright signal that creates a lower signal over here where it's supposed to be straight. So doctors know about Gibbs ringing. They do. They teach them that because they have to be able to diagnose this, okay, and see the difference. Okay? All right. Thank you. Sorry about stealing your time. I explained a little bit about this more. Next week, midterm, Friday.